One of the most pertinent issues facing human-powered vehicles is low cycle fatigue, or LCF. Currently, there are few to no options for monitoring this phenomenon. The 2018 West Virginia University HPVC team is fulfilling the second half of a planned 2-year innovation project that will monitor LCF. The innovation implements strain gauges onto critical points of the human-powered vehicle to monitor low cycle fatigue. The mounting process for the strain gauges is demonstrated here. In the previous year, failures such as inability to acquire real data from riding tests robbed the team of key data that demonstrated the effectiveness of the structural health monitoring system. In order to improve, we conducted vibrational testing with rumble strips, incremental load testings of the boom, and various rider testing. These allowed for controlled testing in contained and real environments. Another difficulty encountered was troubleshooting the software. This troubleshooting made the process more time-consuming than anticipated, but ultimately resolved the issue. For the main testing of the innovation system, the strain gauges were mounted in a half-bridge configuration, as shown here. This is more accurate when compared to the quarter-bridge setup, which was used in testing for the innovation report. The extra strain gauge at 90 degrees doubles the Wisdom bridge's sensitivity, minimizes temperature effects. The physical sensitivity of the wire leads was an issue, as their thin and fragile wires could lead to the system being really easily damaged if not meticulous in the construction process. The other components that lay inside the housing are shown here. The portable battery pack that powers the Arduino is mounted on top of the housing unit. One of the unanticipated negative aspects encountered was hazardous weather conditions, such as rain. Additionally, the low quality of the strain gauges produced many errors throughout the testing process. For boom testing, the loads were increased from 0 to 100 pounds in increments of 25. The recorded strain data of the system is shown graphically. This data was compared to the simulated strain values found in ANSYS under the same conditions. This comparison demonstrates the functionality and accuracy of the design. In order to test the system in a real environment, the stress and strain were monitored while 2 different riders rode the same course. This allows us to see how different riders exert forces on the vehicle in different ways. In the future, this system can be used for professional riders to detect unnecessary deflections to potentially enhance the rider performance. The duration of each rider's drive is highlighted in the data shown. During Rider 1's drive, the conditions were fairly normal and the rider had prior riding experience. Rider 2, however, had little driving experience and was not familiar with the braking system. These hard, abrupt stops caused the boom to be in compression much more frequently. Using the stress-strain curve for chromoly at room temperature, we can see that the strains we recorded were well below the dangerous limit. For future applications, we can implement an alarm to notify the rider when the life cycles or strain become close to low cycle fatigue limit to ensure rider protection.